Welcome. If you're looking to absolutely master your lab skills, you are in exactly the right place. Today's explainer is a two-part mission designed to totally demystify your Class 12 physics practicals. We're going to take the exact materials you'll find sitting right there on your lab bench and break down exactly how to make sense of them. By the end of this, you'll have a rock-solid understanding of two huge tasks: identifying mystery electrical components and mathematically verifying Ohm's law. Let's get right into it. Okay, so here's our roadmap. We'll start with the component sorting challenge, move into visual identification basics, then the multimeter detective test. After that, we'll cover defining Ohm's law, verifying it practically, and finally connecting theory to reality.
Let's kick things off with Section 1, the component sorting challenge.
Imagine walking up to your practical exam station and just facing a chaotic, mixed bag of loose electronic parts. Your first job as an investigator is to somehow make sense of this jumble. Now, I know it might look as confusing as a tangled mess of holiday lights. You've got items that are cylindrical, some look like little water tanks, and others are flat chips with metal pins sticking out. But don't panic. There's actually a super strict logical order to all of this.
Which brings us right to Section 2, Visual Identification Basics.
Honestly, it's pretty amazing how fast you can sort these components just by counting their legs or terminals. You don't even need any testing equipment for this first phase. If you pick up a chip and it has more than 3 terminals, maybe 4, maybe 8, or even more, bam, you instantly know it's an integrated circuit, or IC. On the flip side, if you grab an item and it has exactly 3 pins, well, that's a transistor. Those 3 terminals are just your emitter, base, and collector. Just by counting to 3, you've already sorted out the most complex items in the pile. How cool is that?
Moving right along to Section 3, the multimeter detective test.
So, visual clues are great, but they aren't always enough. Think about it. If a device only has 2 terminals, it could literally be a diode, an LED, a resistor, or a capacitor. Counting legs definitely won't help you here. So how do we tell them apart? Well, this is where we bring in our heavy hitter, the multimeter. We're going to connect these mystery 2-terminal devices in series with a power source and our multimeter and just watch how the current behaves.
By connecting the multimeter, we can observe the current flow, apply some voltage in one direction, then reverse it. If the device only lets current flow one way, meaning you see a deflection in one direction but not the other, and it happens to emit visible light, boom, it's an LED. If it's a one-way street but there's no light, it's just a standard diode. Now, if your multimeter pointer moves no matter which way you apply the voltage, letting current flow in both directions, you've got yourself a resistor. And finally, if you connect it up and the current spikes initially but then quickly decays back to 0, that is a capacitor. That initial spike is just the capacitor quickly drawing a charge. And just like that, you've completely cracked the component sorting challenge.
Let's shift gears to Section 4, defining Ohm's law. Having solved the component mystery, we're ready for our second mission, dealing with one of the absolute most fundamental rules of circuits. Ohm's law states that the current flowing through a conductor is directly proportional to the voltage across it, provided the temperature remains constant. Basically, if the voltage goes up, the current goes up right along with it. They move in perfect lockstep. But, and this is a massive but, there's a crucial physical constraint here. This only works if the temperature stays constant. We absolutely have to account for that reality when we build our lab setup.
Right. Before we actually assemble our circuit, let's just make sure we're totally clear on the SI units we're measuring so our data actually makes sense. Potential difference, which we usually just call voltage, is measured in volts using a voltmeter. And the current flowing through the circuit, that's measured in amperes, or amps, using an ammeter. Time for Section 5, verifying Ohm's law practically.
Let's take the theory off the page and get to the operational phase. When you're setting up your lab bench, you need precise placement for all your measuring tools. The ammeter has to be in series with the circuit to measure the current flow. The voltmeter, though, goes in parallel right across the specific resistor you're testing. You'll also need a battery for your power source, a plug key to open and close the circuit, and a rheostat, which lets us vary the resistance and thereby change the current. Oh, and a major pro tip here. Make sure all your electrical connections with those sandpapered wires are neat and incredibly tight. You really don't want to introduce any accidental resistance.
So here is how you actually execute the experiment. First, adjust the rheostat slider to get just a small initial current reading and record both the ammeter and voltmeter readings at the exact same time. Then, you're going to gradually adjust that rheostat to change the current, taking multiple pairs of readings. You want at least 5 or 6 sets to get solid data. Now, remember what we said about Ohm's law and temperature? Here is the absolute most critical part of your lab technique. Only insert the plug key while you are actively taking a reading. If you leave that key plugged in, a large current is just going to keep flowing, it'll overheat your devices and completely ruin the accuracy of your results. Seriously, keep an eye on that key.
Which brings us to our final part, Section 6, Connecting Theory to Reality.
This is the climax of our explainer, translating all that messy lab data into a beautiful mathematical proof. When you plot your 5 or 6 sets of readings on graph paper, usually putting potential difference on the x-axis and current on the y-axis, you are going to see something deeply satisfying. If your setup was correct and you didn't overheat your wire, those points will form a perfectly straight line. Even if a point or two is slightly off, the overall trend will be entirely linear. That resulting straight line graph visually verifies Ohm's constant proportional relationship. But hey, the graph isn't just a pretty picture, it is hiding some serious mathematical data. Because we plotted current against voltage, calculating the reciprocal of this straight line slope actually gives us the exact resistance value of the wire.
Let's put that into perspective with a real-world example. In one practical demonstration, a student took their graph, found a voltage change of 0.8 volts and a corresponding current change of 0.65 amps. Dividing those numbers gave them a real-world resistance of 1.323 ohms for their specific wire. Now, keep in mind your school's specific resistance wire is going to have its own unique reading, so your final number will definitely be different. But the methodology, that stays exactly the same.
Take a second to think about what you've just accomplished. You now have the analytical skills to look at unknown components, interrogate them, and mathematically prove the laws that govern them. The smartphone in your pocket, the computer you use every day, they are entirely governed by these exact same principles. Now that you've got the fundamentals down, what kind of everyday electronic mysteries will you investigate next? Keep exploring.